Let's discuss Unit 2 solutions. A processor chip is used for application in which 30% of execution time is spent on floating point addition. For the new model of the processor, the design team has come up with redesigning the floating point adder to make it twice as fast. What will be possible maximum speed up by this redesign? There is a law to calculate the speed up process. The law's name will be Amdahl's law. This is used to calculate expected system improvement when parts of the system are improved. Redesigning the floating point adder is the part of the system that needs improvement because we have to make it twice as fast. Speed up is equal to 1 divided by 1 minus f plus f by n. What is this f? This is the enhanced fraction and n will be the speed up factor for enhanced fraction. Here the enhanced fraction will be 30% of execution time. So we assign 30% to f. 30% can be written as 30 divided by 100, which is equal to 0.3, and n is equal to the speed up factor. So how much speed they have mentioned here in the question is make it twice as fast. So whatever the speed is, we have to just make it twice. So twice as fast can be represented using the number 2. So we'll apply these values in speed up formula. Speed up is equal to 1 divided by 1 minus 0.3 plus 0.3 divided by 2. 1 minus 0.3 will give 0.7. 0.3 divided by 2 will give 0.15. 0.7 plus 0.15 will give 0.85. You will end up with 1.1765. This can be approximately equivalent to 1.18. Option number 3 will be the right answer. Next question. What is the 4 plus 4 fit binary fixed point equivalent of minus 3.72 in decimal format? This is in decimal and they are asking in binary format. Here you have 4 bits before the point and 4 bits after the point. So that's why they have asked in 4 plus 4 fit form. What is the actual process of finding the negation of some floating point number? We will see the process first. For this floating point or the decimal point, if there is a number, first we have to convert decimal to binary. Next we have to take ones complement of the answer, and the third step will be we have to add 1 to the answer of the second step. Ones complement is you have to change all your zeros to ones and ones to zeros. In 8421 format, I will have 0011. So 0011 will be equal to 3 in decimal. If you see all the 4 options, almost 1, 2 and 4 all have the representation of 3. But once you negate this number, you have to apply ones complement. At this stage itself, this 3 will become 1100. So without referring this 0.72 part, we can easily say option 1, 2 and 4 are wrong. Option 3 will be the right answer. Now we will just solve it using the steps written here. The first step is to convert decimal to binary. So here's a whole number 3 and we have a point here. 3 in decimal will be converted to 0011 in binary. Then 0.72 in decimal. So how will you convert this into binary is you have to keep multiplying it by 2. Say for example 0.72 into 2. This will give 1.44. Now this digit before the point will be mentioned here. Now you have to take this 0.44 alone. You have to take this in the answer part and this for further multiplication. So I'll just take 0.44 into 2. It is 0.88. Now we'll mention the 0 here. Then 0.88 into 2 will give 1.76. Again mention 1 here. 0.76 into 2 will give 1.52. So mention the 1 here. 0.52 into 2. Make sure you go for 6 or 7 digits of binary value. Though they have asked only 4 digits after the point, we'll just go for some 6 or 7 values. So 0.52 into 2 will give 1.04. Again we have 1. 0.04 into 2 will give 0.08. 0.08 into 2 will give 0.16. So we have two zeros here. I think we can stop with this. Now the value of 3.72 in decimal will be 0011, 101110, and it goes on in binary. Actually, you cannot end this binary form of 0.72 because after some iterations you will have 0.88 again. Then the same thing will come around again. So we are stopping with this. Now this will be the first step. The second step will be applying ones complement. So 0011 10111100. Just apply ones complement here. It means I have to change zeros to ones and ones to zeros. 1100 010011. Now I have to add 1 to this. So 1100.01. Let's stop with 5 digits here and just adding 1. 0 plus 1 will give me 1. 0010. Then we have 0011. This will be the binary fixed point equivalent of minus 3.72. This is equivalent in option number 3. Making it for 4 plus 4 binary fixed point, this will be 1100 is 4 bits. We just take only the first 4 bits here. So 0100. Why I am stopping with the fifth bit here is only this will be counted for the end result for this question. Actually, you cannot take only 4 bits here and add 1. This will ultimately disturb this position here. That's why we are taking extra bits after 4 and then adding 1 there. Since 0.72 runs long, adding 1 to 1's complement will not affect first 4 bits. For 3.72, this will be the answer, and you can find this answer almost equivalent in option number 4. Option number 1 will be 3.75. Option number 2 will be 3.625. This is actually in positive form and this is in negative form. Next question. 256 MB dynamic RAM is organized as a 32 M into 8 memory externally and as a 16K into 16K square array internally. Just take a square. You have 16K this side and 16K this side. This is externally and this is internally. Each row must be refreshed at least once every 50 milliseconds to forestall loss of data. Forestall in the sense you can take this as prevent, in order to prevent loss of data. Refreshing one row takes 100 nanoseconds. What fraction of the total memory bandwidth is lost to refresh cycles? Rows are refreshed once in 50 milliseconds. Refreshing one row takes 100 nanoseconds. So just consider them to be an array. You can understand the row and the column format. So this will be 1, 2, 3, 4 columns and this will be the rows. So you have 16K rows. So refreshing 16K rows will take 16K into 100. So this K can be taken as 1024 into 100 nanoseconds. And here 16 into 1024 will give 16384 into 100 nanoseconds, which is equal to 1638400 nanoseconds. Since they have given each row must be refreshed at least once every 50 milliseconds, we have to convert this nanoseconds to milliseconds. Nanosecond to millisecond conversion will be approximately equivalent to 1.6384. Nano is 10 power 9 and milliseconds will be 10 power 3. Ultimately, you have to reduce to 10 power minus 6. So you have to move 6 positions. 1, 2, 3, 4, 5, 6. That's why I have placed the point in between 1 and 6. So why I am moving 6 position is because I am converting nano to milliseconds. So minus 9 plus 3 will give me minus 6. That's why it is moving in this direction. Refreshing process of 16K rows will take 1.64 milliseconds. So I am just approximating it, 38424. What fraction of total memory bandwidth is lost to refresh cycles? So loss of 1.64 milliseconds every 50 milliseconds. This will give 1.64 divided by 50. This will give 0.0328. And since they have represented the answer in percentage, we are just multiplying this by 100 and this will give 3.28 percentage, which is approximately equivalent to 3.3 percentage. This much will be lost. So option number 2, 3.3% will be the right answer. So this diagram is actually incomplete here. Let me give you in short. This is 16K this side and 16K this side. We'll have a row decoder here. We have a row buffer here and we have a column multiplexer. This is for data out. This was the glimpse of the diagram that I have got. Next question. Let the symbol denote XOR operation. Let 1 and 0 denote the binary constants and F is the Boolean expression over two variables P and Q. Let's take P and Q as a truth table here. 0, 0, 0, 1, 1, 0, 1, 1. What is P XOR Q? Whenever we have same input, we get 0. Whenever we have different input, we get 1. This is the case of XOR. So the condition for 0 will be P into Q, P naught into Q naught. And to get 1, we'll have P dash Q plus PQ dash. And this will be XOR and this will be negating the XOR. Before getting into this question, we will find this. P XOR Q is fine. You have something called 1 XOR P and Q XOR 0. So what happens when I XOR something with 0 or 1? So let's take P XOR 0. This is equal to find the XOR I have to use this format. So here it is P for me and 0 will be Q. P bar 0 plus P into 0 bar. This will give anything into 0 is 0 plus P into 1. This will give P. When I XOR 0 with a variable, I get the variable. So P plus 0 will give me P. 0 plus P will give me P. Q plus 0 will give me Q. You have XOR with 1. So what is P XOR 1? So P bar into 1 plus P into 1 bar. P bar into 1 will give P bar plus P into 1 bar is 0. So the complement of 1 will be 0. Anything with 0 is 0. So we will end up with P bar. So P XOR 1 or 1 XOR P will give negation of P. The same thing applies for Q. XOR is commutative and associative. And there is also another rule. If you take an element P and if I do XOR operation with P again, this will result in 0. How does this happen? A small proof. So P XOR P will be P into P bar plus P bar into P. 1 into 0 or 0 into 1 will give me 0. This way we are bringing 0 here. So always remember any variable that is in XOR operation with the same variable will end up with 0. Now let's solve this. 1 XOR P will result in P bar. XOR this P XOR Q will stay. XOR P XOR Q will stay the same. This XOR here and Q XOR 0 will give Q. Let A is equal to P XOR Q. So how will you change this is A XOR A. What is A XOR A? It is 0. So the whole expression here will become 0. So P dash XOR 0 XOR Q. This 0 is because we are taking let A is equal to P XOR Q. Any variable that has XOR operation with the same variable will end up in 0. Now anything with 0 will give the same variable. So this will be P bar XOR Q. First we have to take this to be P and take this to be Q. P bar will be P bar Q plus P bar will stay and then you are negating Q. So I have two negation here. I am cancelling it and bringing to PQ plus P bar Q bar. It is in the form of negation of XOR. So now I can put this as P XOR Q and whole negation will be applied. It is because we are getting the results of 0 part. Option number 4 will be the right answer. All these things must be in mind before you start this problem. Next question, match list 1 with list 2. What is A delta B? Let me represent it using a Venn diagram. So take this to be A and take this to be B. Except the intersection part of AB, delta covers everything. It has everything except A intersection B. You have two formulas. The first formula will be A union B difference A intersection B. So I take the whole of A union B and I am just removing the intersection part alone. That gives me A delta B. The other formula to represent this will be B minus A union A minus B or A minus B union B minus A. B minus A will give everything in B but it will exclude only A, and A minus B will include everything in A but it will exclude B part alone. The A intersection B part will be excluded in total. If you find option number 3, A minus B union B minus A, this formula is given here. So A is mapping to option number 3. A with third option is option number 1. So this will be the right answer. So let's work out B. A minus B union C. Now we have to apply this set difference operation to the variables inside. So this will result in A minus B, A minus C. So what will be the operator in between is this union will become intersection. So B will be mapping to 2. Let's take C, A difference, B intersection C. The same thing, A minus B will be there, A minus C will be there. Instead of intersection, we will have union. So first option will be for C. Then D. A intersection B minus C will give A intersection B, A intersection C, and we'll apply the difference here. So this is equal to option number 4. Next question. This is actually based on the topic virtual memory. These questions can also be placed in operating system unit, unit 5. So for video length purpose, I am just placing it in computer system architecture unit. Now let's get into the question. Consider the following program fragment that deals with a table T with 17 rows and 1024 columns. So the number of elements that it has will be 1024 into 17. It is 17408. These many elements are present. Computing an average for each column and printing into screen. So they have given two for loops. One is counting rows and another is counting the columns. Since columns are given a number of 1024, the first loop mentioned here counts the columns and the second loop is counting the rows and it is printing to screen. I is row index as I have already told and J is column index. So what does this program do is it is just starting with J loop. It is initializing a variable called temp with 0. Then I have an inner loop with I 0 to 16. So 0 to 1023 will give 1024 columns and 0 to 16 will give 17 rows. You know the index will be starting from zeros in arrays. So they have used the same pattern here. Now there is a simple calculation. Temp is equal to temp plus, that is 0 plus the element from the table T. If we want to access some element, we have to access the particular row and the particular column. So this is T of I and j. After accessing the element, so here they have given computing an average for each column. So a print statement is here. Table with index ij and temp are 32-bit floating point values and memory is word addressable. The temporary variable temp is kept in a processor register, so access to temp does not involve a memory reference. You need not access temp from the main memory. The main memory is page and holds 16 pages of size 1024 words. So the number of pages will be 16. Words per page will be 1024. The page replacement policy is least recently used. If T is stored in the virtual address space in row major format, whenever we want to store a table, there are two ways of storing it. One is in row major order and the other is column major order. So the subsequent questions will have column major order. I will explain column part in that question. This part is row major format. So when you take a table with row major format, you will have something like this. This is row 0, 1, 2 and this is column 0, 1, 2. When I say it is 0, 0, 0, 1, 0, 2, the access will be going row wise. So if I take a row, I'll access everything and then I'll go to the next row. Column wise access will be, I'll access the complete column and then I'll go for the next. This is in general about a row major arrangement and a column major arrangement. Now the first question is, how many page faults will be encountered for j is equal to 0 to 1023 and for I is equal to 0 to 16. So if you take T, this 0 will stay. This is I and this is j. This j will stay and the ith index will have the change 0, 1, 2, 3, 4 and everything will have 0th column here. It means I am accessing it in this way. The first element will be 0, 0. The second element will be 1, 0. Here every row takes one page. One row has 1024 columns. It means 1024 elements are present in one page. Because a page has 1024 words and the memory is word addressable. All these are information in the question. Since every row takes one page, one word in one page is printed. So if you take first 0, 0, it is printed in 0th page. 1, 0 is printed in first page. 2, 0 is printed in second page. Whenever I access a new row, it means I am accessing a new page. So how many times I access the pages? For one column, I am accessing 17 pages. What about 1024 columns? I will be accessing 17 into 1024 times. So for printing content from one column, I am referring 17 pages. Why they have mentioned least recently used is, if I take page 0, am I printing everything from page 0? No. When I take page 1, am I printing everything from page 1? No. For printing one element, I refer one page. So for printing 17,408 elements, I have to reference every page every time. It means the number of page faults will be 17 into 1024, which is equal to 17,408. Option number 2 will be the right answer. So let me again tell you, take this to be word and take this to be the page. 0th word in 0th page, first word in first page, second word in second page, it goes on. So after completing 16 pages, then I have to start with 0, 1, 2 again. And the word will be continuing till 1024. So least recently used means whatever page I referred before, that page has to be referred again. This loop does not give that possibility. For that reason, I am accessing a new page every time I access a element. So here accessing this table is alone taken into consideration because temp is kept in a processor register. It does not involve a memory reference. I am considering only the table access. I take the first column, I refer all pages. I take the second column, I refer all pages. So for 1024 column into 17 pages, this is the calculation that we do. So for every element, I am accessing every page. If I place the element in the same page, then the page fault will be reduced. If I don't access the same page, then the page fault will be increasing. I hope you understand this. Maybe the subsequent questions will make it clear. Next question, what is the main memory hit ratio? First, let's understand what is hit ratio. Now let's take least recently used. Let me take a frame size of 3. Let's take 2, 1, 2, 3, 2. So first I am placing 2. So this is a page fault. Then I am referring 1. So this is a page fault. This is how we will be calculating in page replacement policy, right? Now I have 2 again. I will not place it, but I will take the same reference. Now again I will be referring a new page. So 2, 1, 3. So here there is a fault. When I am referring the same page that is already in the memory, it is called as hit. Hit means the page is referenced from the main memory. If there is a page fault, then I am taking it from some other place. I mean, like the secondary memory has to load it in the main memory and then it has to be referenced. Whenever there is no page fault, there will be a hit. This is hit in context of main memory. What is generally hit ratio? The number of hits divided by the number of hits plus miss. The hits will be the number of references made. So this miss will be the page faults. So hits divided by hits plus the page faults. So overall, how many hits plus misses will be there is, you have to take the overall count. All the elements will take 17408 and how many hits are there? Every time I am referring a new page and still it is in row major format. So for each row, I take one page and so there are 17408 page faults. All the elements are using new page. In this case, the number of hits will be equal to 0. I mean no page is referenced again. In case if there is a hit, then there will not be any page fault. Fault is bringing them inside and hit is using what is already inside. Here the false will be 17408 along with 0 plus 17408. This will give 0 by 17408, which is again 0. 0 by anything is 0. Whenever the CPU references the memory, we call it as hit, and whenever a page is brought to the main memory, we call it as fault. That's why I gave you this example. Again, just we'll continue the same example. So 2, 1, 3, I am referring 2 again. I am not bringing any new page. So this is again a hit. So regarding these 5, I can say the hits is equal to 2 and the false is equal to 3. So the ratio will be 2 divided by 5. This is how we will be calculating. So the same case I am applying. There are 17408 page faults and there are 0 hits for 17408 elements. So when there are 0 hits, 0 by anything will give me 0. So what is the main memory hit ratio? Option number 1, 0 will be the right answer. In row major format, there are 17408 page faults for 17408 elements. In this case, there are no hits. Therefore, hits is equal to 0. That's why hit ratio is 0. Next question. Consider that T is stored in column major format. How many page faults will be encountered? For I is equal to 0 to 16, temp is equal to 0. For j is equal to 0 to 1023, and then the access is taking place and printing is taking place. We usually create array keeping for row index and for column index, but they have given in for column index to row index. Now column major format, you have to just swap column part and row part in the loop. So I am placing the row part here and the column part here. So let's take the T is stored in column major format is this part. How many page faults will be encountered? So for I is equal to 0, whenever I is equal to 0, how many elements can be accessed is 1024 elements can be accessed. So when I is equal to 60, 1024 elements can be accessed because the inner loop has the column count and the outer loop is having row count. As we already saw, each row takes one page. How many pages are referenced here is 17 pages are referenced. When I take my first page, I take 1024 elements. When I refer second page, 1024. Similarly, in my 17th page, I take the last 1024 elements. T of 0, 0, 0, 1, and then this is 1, 0, 1, 23. So in this way, this is row 1. In other way, I can say this is page 1. So keeping page 1 in memory, I can access 1024 elements. Keeping page 2 in memory, I can access 1024 elements. So only for 0, 0, I am accessing page 1. From 0, 1 to 0, 1023, I am just using hits of page 1. In list recently used, I gave an example. When there is no page fault, I said there will be hits. So here one page fault occurs and 1023 hits occur. When I bring in the first page to the memory, it is page fault. When I refer it again and again for the rest of the element, it becomes hits. If T is stored in column major format, how many page faults will be there is, the number of rows will be the number of pages here. So totally 17 rows means 17 page faults will occur. Option number 4, 17 will be the right answer. So for all 17 408 elements, we need only 17 page faults because every page is having 1024 elements. When the outer loop is column, page faults are more. When the outer loop is row, page faults are less. Next question. Consider again that T is stored in column major format. What is the main memory hit ratio? In column major, I said first we'll have ith row from 0 to 16. Then we have inner loop jth column from 0 to 1023. I told you the page fault for page 1 will be 1 and the hits will be 1023. This means for 1024 elements, I have 1 page fault and 1023 hits. For this alone, I can calculate like hits is equal to 1023 divided by hits plus faults or hits plus miss, whatever you understand. So 1023 divided by 1023 plus 1, which is equal to 1023 divided by 1024. This will give me 0.999, and when you multiply it by 100 to bring it to percentage, you will get 99.9%. Option number 4 will be the right answer if you want to take it in a detailed way. For 1024 elements, I said there are one page fault with 1023 hits. This is in the case of one row. What happens when there are 17 rows? So we'll say 17 page faults plus 17 into 1023 hits will be there. So in this case I can say hit ratio is equal to the number of hits will be 17 into 1023 divided by, so 17 into 1023 will be here plus page faults. So 17 into 1. Keep the 17 in the numerator as it is and bring the 17 outside. So there are 17 page faults. Instead of keeping it as 17, I am just marking it as 17 into 1. Or you can just place it as 17. So cancelling the 17, you will again end up with 1023 by 1024. This is the actual way of mentioning it. With just one page, I have mentioned like this. For one row count and for 17 rows, I have explained in this way. Certain people can also do this in other way. For accessing 1023 elements in 17 rows divided by accessing 1024 elements in 17 rows. This ratio will be 17391 divided by 17408. So this is another way of writing. Whatever you write, you will end up with 99.9%. Why I am giving way 1, way 2 or way 3 is all these three explanations are same. So first I am calculating only for one particular page. I am just separating the page fault and hits and doing this calculation. I have done this way. To consider all the 17 pages together, I did this way, and to do it based on the elements, like the hits will be the number of elements accessed, right? So out of 17408, if you take 17 elements, because for the first page fault that element will be accessed, if you take, you will end up with 17391. So 17391 elements are accessed from the memory out of 17408 total elements. The next question, what is the fault ratio of row major to column major arrangements? The page fault we had during row major, the 91st question had 17408. How did we end up with this 17408? It was 17 into 1024. How many page faults were there in column major? That is the answer of 93rd question. It was 17. Now they are asking the fault ratio of row major to column major. So just place row major is to column major. Now you can mention as 17 into 1024 is to 17. I am just placing this way. So 17 gets cancelled. So 1024 is to 1. Option number 1 will be the right answer. When you have lots of time, you divide 17,408 by 17 and bring to 1024. It's your choice. With this, we are completing Unit 2 questions.